Bonjour à tous, merci et bienvenue à ce Performance User Group. Alors quelques petits slides pour introduire comme d'habitude. Aujourd'hui, on a le plaisir d'accueillir David de Couchbase qui va nous parler de la performance de Couchbase en rentrant dans les détails techniques. Et puis ensuite, questions-réponses et puis un petit pot que maintenant on aura la chance de pouvoir avoir au même étage, donc directement après la présentation. Un petit mot pour le sponsor, on est toujours chez Octo, même si les locaux ont changé depuis la dernière fois. N'hésitez pas si les sujets vous intéressent, si vous avez envie d'en savoir plus. On embauche, on a également des formations sur la performance, mais également sur la partie nouvelle architecture de données, et notamment sur Couchbase. Un petit clin d'œil notamment à l'équipe NAD. Normalement, il y a quelqu'un que vous devez reconnaître dans la salle. Tu veux ajouter quelques mots pour raconter ce que vous faites? En deux mots, c'est l'équipe Nouvelle Architecture de Données qui s'occupe de tous les systèmes de stockage distribués, dont Couchbase. C'est eux qui font les formations chez Octo, c'est eux qui viennent vous aider sur Couchbase si vous en avez besoin, d'où un intérêt supplémentaire aujourd'hui. Voilà, le prochain PerfUG sera fin mars, on vous annoncera ça comme d'habitude sur le Twitter. Et maintenant, je vais laisser la parole à David pour rentrer dans les détails techniques. David.
Ah. Merci. Merci. Parlez-vous anglais? Je suis désolé, je vais parler en anglais. J'étudie français et j'étudie l'informatique, mais je n'étudie pas l'informatique en français. So, je ne sais pas performance at high scale en français. C'est très difficile. Aussi, votre anglais est très supérieur à mon français. So, je vais parler en anglais. Okay. My name's David. I work for Couchbase, based in Manchester in the United Kingdom, and been with Couchbase about three and a half years. Before that, I was at IBM and then another startup. I managed the engineering team there, the engineering team that's responsible for the Memcache D component, the key value component of Couchbase. We'll talk a bit about what that means. Just maybe like to quickly start with a show of hands. How many people in the room are familiar with NoSQL? Fantastic. That makes for a very short introductory section. How many people have actually used a NoSQL product in anger? Okay, very good. And now the killer question, money riding on this. How many people have used Couchbase? Oh, man. Excellent, and one at the back as well. Okay, very good. So what I'm going to do, and I need to check with how long I've got to take you through this. A talk in 4 parts. I know this is the Performance User Group, and thank you very much for inviting us to speak today. It's a pleasure to be here in Paris. It's a lot drier than it is in Manchester. So a very quick skip through of what we as Couchbase think NoSQL means about performance. Then a little bit about Couchbase itself. For those of you that have never, only a couple of you that in the room that had never tried the product, just talk you through some of the features. Not so much this is a sales pitch. I'm not here to try and sell you or twist your arm into buying Couchbase, but some of the things I need to say about the features that Couchbase has will have a bearing on when it comes to the interesting stuff when we talk about performance. Then the third part, that's the area that's closest home to me, is the key value performance, the component that I'm ultimately responsible for. And I'll try and spend as much time as possible with an actual live demo. I'll confess now, I haven't spent a lot of time rehearsing the demo, so anything could happen. So hopefully we'll have a little bit of fun. So we'll start with a very quick skip through NoSQL. So obviously, relational database technology has been around for the past 30, perhaps 40 years. It was invented at a time where disk was very expensive and very rare. Memory was very expensive and very rare. And there was an art in storing your information in the smallest footprint possible, the least amount of space, the game of normalization. So saving duplicate entries by having keys to entries in other tables that would quickly look things up. And that stood the database industry in very good stead for many, many decades. And it's still the most common and the most popular database technology that you see around today. But it brings with it challenges, like fast forward to the modern day where everybody has a smartphone, maybe a tablet, maybe a laptop. There are more people online with more devices connected online, and they're spending more time online. So from your phone you can order a pizza, order a taxi, do your expenses. You can even find a partner online these days with a swipe of your thumb left or right. And all of this is generating data. And the users today are more demanding than they've ever been. Nobody likes to see the spinning circle waiting for content coming down. Everything needs to be instant. If it takes too long, you'll go elsewhere, you'll switch off, you'll go to a competitor, you'll buy from a different site, you'll tweet something else. And so that's one of the big advantages that NoSQL has, is moving away from this tabular relational structure where to get at the details, like take my user profile. When I log into Amazon, it knows my name, my address, my preferences, my purchase history, etc. All this information. And if that lives in separate tables that you need to query and then join together, that takes time. It takes time to say, okay, David Hackney, he needs his user preferences from over here, his purchase history from over there, his details, his credit card, etc. Glue them all together so I can present the website that looks like his own customized page. Far simpler if you just, now that space is cheap, disk is cheap, memory is cheap, you don't need to work so hard to minimalize the amount of data you store. And far quicker if I can just log into a site and say, hello, I'm David Hackney, and there's a single document that represents my information, and I can just say, here's my key, i.e. my username, my email address, etc. Give me the document that represents my details, and the database returns and responds and says there you go. That's one of the key reasons that NoSQL is faster. There's also a granularity advantage to be had with this. Imagine if you've got tables that hold details for everyone, information for all of your users, all listed in a single table. Accessing that in a safe fashion requires you to lock some portion of the table. Whereas now, if all of my information is stored in a single place, a single document, I can get at that, I can do what I want with that single document without worrying about having to lock content for other people and have instant direct access. So there's some architectural advantages that we can leverage in the underlying database by the fact that we've moved to a document model. So a quick bit of fun. You put all this together, more users online, more often accessing more apps. This is what happens when this coincides with the real world. Quick bit of video here. Does anybody recognize this particular bit of video? Yep, do you know where this is taking place? Central Park, New York. And they're all looking for a particular Pokemon. Right, bonus question, does anyone know the kind of Pokemon they were looking for? It's called a Vaporeon, I believe. And so I use this as a little bit fun because this is, so these people, it looks kind of like some sort of zombie stampede. So this was Pokemon Go, the huge event of last summer where they launched and it went the most downloaded app ever, the most number of concurrent users ever, etc. And this is when they put a very rare Pokemon in the middle of Central Park, and all of the people that had collected most of them but didn't have this one sort of rushed off. And this is kind of this embodies the points that we've just spoken about there, that all of these people have all got a device in front of them, they're all online, they're all logging in, it's all doing that transaction of pulling down their details. And this is a nice example for NoSQL and where it's applicable. And yes, I'm happy to say that Pokemon's registration did of course use Couchbase. But there are many other examples, and I'll just throw a few up here. So at least one or two Pokemon players. Have anyone in the room that watches Game of Thrones? Yeah, A few more. But Game of Thrones, more popular than Pokemon, according to this demographic. So for broadcasters, now that you've got access to live streams of content, many television providers in the UK, companies like Sky, British Telecom, BBC, offer access to their live streams. And so events like big sporting events like the Six Nations rugby matches or the Champions League games or the new season of Game of Thrones, more people are reaching for their iPad or their phone on the move to log in. And what the broadcasters see against their database is a huge spike of incoming connections. The season premiere and the season finale of Game of Thrones are huge events. Another favorite of mine. So I have two children. One's 5, one's 7, and one day a year I let them gamble. I let them place money on horses. I don't do it all the time, just once a year. So in the UK we have the Grand National, a huge horse race where for about 40 minutes, about 50 horses run around this track somewhere in the middle of England, and a single horse wins. And for some reason it's the day that nearly everyone has a little bet, like 50 pence or €1, something of that accord. And again, if you're a gambling site, the Grand National, some of the gambling sites see 30% of their annual traffic over that weekend. And it's not just everybody placing bets, it's the people looking for the names of the horses, which one's got the nice colour that they like, the name that they like, which one's a good price before actually placing the bet. So there's this weekend in the middle of April that's a huge weekend for a certain small set of companies. And of course, again, they want an infrastructure that's ready to cope with the demand that's placed on it. Travel is another one. So more and more these days, when somebody wants a holiday, you'll go to somewhere like Expedia or Kayak or Skyscanner. And you very rarely, I find, go to these sites with a particular flight in mind. You want to know what's cheap, where can I go, what's the best time to go, what are the different prices, what are the different locations. So you might, if you're planning a holiday, you might do hundreds, maybe even thousands of flight searches. You never get, also when you pump in the details, you never get back a single result. You get all of the different options. So imagine behind the scenes, there's a piece of infrastructure that's serving responses to all of those requests. A cluster of database nodes that's handling millions of these lookups, millions of these transactions a second. And again, this is a nice fit for NoSQL. Very topical tomorrow. Hope many of you will be sending or maybe getting a Valentine's card. And so for relationship websites, places like Match.com, they do huge promotions around this to try and encourage new users, additional connections, etc. And again, they're a tremendous spike in activity. One thing that's more exciting than love, tax. So this is an example from the UK where you can submit your tax return online, and the tax return deadline is the 31st of January. So when do most people in UK submit the tax returns? It's in that 30th or the 31st of January. So again, they have a steady rate of traffic throughout the year, then an enormous spike where everyone's trying to get their submissions done just before the deadline. And of course, a huge one for Couchbase is retail. So a couple of events throughout the year. Black Friday, this big US phenomenon where they have promotions and sales, and or Christmas Day. So customers of ours, when you get your new phone, you're downloading apps for the first time. And all of these, the registration services, the app, the content providers are getting hammered with requests. And all of this information needs to be stored and tracked in a database. And we find for these kind of use cases, NoSQL is a better fit for than Relational. A quick example of what happens when it goes wrong. What happens if you've not done your homework on your performance? What happens if your infrastructure is not ready? And so this is a real screen capture from, I think it's 2015, a UK retailer on Black Friday. And just look at this message here. So you've gone onto a web, this is 2015, you've gone to a website and it says, really sorry for the delay, please wait 9 minutes, 9.5 minutes. It's crazy. Like, who's going to do that? Of course you're not going to wait 9.5 minutes. Maybe you will. Maybe you'll go away and come back. But chances are you're going to look for details, look for the deals on somebody else's site. And so this is something Couchbase works very closely with its customers on, is making sure that you're prepared, you've done your homework, that your infrastructure is capable of the performance requirements that events such as these are going to place on it. And this is the story that we want people to be having, that, okay, yes, you had this peak event, it was the biggest day of the year for you, and it went very well, and your sales were all well and good. So that's a quick introduction of where we see the strong overlap between NoSQL and performance. No matter what industry it is, we've covered a handful there. Each one of them has these requirements that can tend to very sort of high peaks of workload, where you need your infrastructure. And it's not just your database, it's obviously all of the other components, your web tier, and all of the application logic, and all of the hardware, etc. But all of that is crucial to make sure it stands up for the big event. Now, quick flavor of Couchbase and what Couchbase offers. Obviously, there are many different NoSQL solutions out there. And so here's it's a lot of text. There's a lot of reading on this. I'll try and demonstrate some of it. So what is Couchbase? It's first and foremost, it's a document database. So you, as I just described, you put things in using a key and a value. The value can be anything, a binary blob, or it could be a JSON document. If it is a JSON document, you can do some interesting things with it. We can interrogate the contents, create indexes, etc. Couchbase operates in a clustered fashion, so you group multiple nodes together. What this means is that when you send a document to the database, it will replicate it to one of its peers in the cluster. That means if that primary node for that data goes down, then the replica copy can be promoted and your data is available even if your hardware has failed. Now, using this same technique of spreading out the data and copying bits of data around, we can also use that same technique to dynamically grow the cluster. So in Pokemon's case, where they started in the US with 20 nodes of Couchbase running in their cluster, we saw the traffic sort of keep increasing. We said, "Oh, what's going wrong?" And they would tell us, "Oh, we've just launched in Germany today, or next week it's France, or now it's the UK." And as they did this, they added more nodes to their cluster without bringing the service down. So you can keep a replica copy up to 3 times. We have the ability to send an entire copy, excuse me, of your data set across offsite to an entirely different cluster. So for proper disaster recovery, we call this XDCR, or cross data center replication. Now, here's where we bend the rules a little bit on NoSQL. So NoSQL, we dub not only SQL. In a couple of releases ago, we introduced we found that our users were, okay, we like this key value access pattern, but actually I've spent a lot of time at university or in my job writing things that look a lot like select star from this or look up this field. A lot of people out there are obviously intimately familiar with the SQL syntax, and they like that familiarity. So we provide NQL, we pronounce this N1QL, which is a SQL-like syntax for JSON documents. So you can do select age from document where user equals X. That's right. So for those that are transitioning from the relational world or need to run queries across their JSON document set, and with that, in order to get the performance, you need an indexing capability. We also have a full text search. So a common use case is to export your data to a separate search engine, something like Elasticsearch. And often we find that customers are doing that for reasonably simple queries, just to show me all of the documents that match this quite simple search term. So something that's in developer preview at the moment, and we're going to make generally available in the next release, is a full text search capability. So you have all your documents there in Couchbase. Let's just create a full text index on them so that it does all of the word manipulation. So if you search for engineer, it also finds engineers and engineering, etc. It's that slightly richer full text match. We have what we think is a pretty novel mobile capability. So for those of you developing mobile applications, there's a challenge that every mobile developer faces is, what do you want the application to be able to do if the user's not connected? Now, what if the application is offline? You've got a couple of choices. You can allow them to manipulate their data locally on the device, and then you've got the challenge of, well, when they come online again, what do you do? Do you discard that copy? Do you synchronize that copy? In which case you're in the business of writing your own synchronization protocol. Or maybe, as some recent games have done, you just prevent that capability in its entirety, which is a little bit sad and a little bit crazy that if your phone's not online, that you're denied access to play the game or run the app, etc. So this is something that Couchbase provides. We call it the sync gateway, so that if you do have your mobile device offline, you can change and modify your data locally, and we'll provide that protocol that allows you to merge it with a centralized copy. And developer kits for most of the common popular languages. So always interested actually in a quick straw poll in which languages people are developing in. Historically, I was a C++ developer, but it seems to have fallen by the wayside. A lot of the people who speak to are into Go these days. Any Go developers here? And a thumbs down at the back. Wow. Java? Still a lot of love for Java. Java's never going to go away. .NET? A few .NETs. Python? A lot of Python. And any PHP? Oh, still some PHP. Cool PHP. I spent a lot of time using Perl, and it seems to become a little bit obsolete in the work I do now, which is why I'm very hesitant to adopt Go. Maybe if it's still around in 10 years' time, I'll think it's ready to have a look at. Okay, so I'm just going to touch on one of these concepts in a little bit more detail, that of automatic sharding. So I mentioned that Couchbase operates in a clustered fashion, and so we provide developer kits in all of those different languages. And so in order to get the performance, we need each of the servers in the cluster to operate in a very even fashion. We don't want any hotspots. We don't want one server that's doing more workload than any of the others. And so what we try and do is spread the data evenly across the cluster. We use a simple hash function, a CRC32 hash, and we have a layer of indirection which is this map here that I'll talk you through. So in Couchbase, we put all of our documents in it. We call it a bucket. So if you want to store something, you choose a bucket to put it in. It's just basically a label or a container around a set of documents that you might want to stick together. Now, behind the scenes, we split this bucket into 1,024 pieces, and we sprinkle these 1,024 pieces across the servers. So in this diagram here, I've got 3 servers in my cluster. So each of those servers will have 1,024 divided by 3 of the virtual buckets, these small pieces across it. Now, we create a map that we give to our developer kit. So this is all handled by the libraries that we provide. We create a map that says where each of those little shards, those little vbuckets, which server they rely on. So you'll have a map that says something like vbucket2 lives on server C, vbucket27 lives on server B, etc. And then what we do, if you want to write a document to Couchbase, so say in this case I've got the hello octo, that's my key, that's the thing I'm going to hash. And so we run a CRC32 hash function, which will tell us the vbucket. In this example, this is hashing to vbucket27, which our developer kit looks up in its map and it goes, okay, vbucket27, shard27 lives on server B. A very simple level of indirection. The hashing function is consistent across all developer kits, across all libraries. So anywhere you go, when we apply the hash function, that hello octo will always go to vbucket27. Very, very consistent. And what this means we can do is if we want to expand the capacity, say I've written a new app, it's going to be the new Pokemon, and I think, oh no, 3 servers just isn't going to cut it. I need 4. What we can do is, without taking the application offline, we can introduce a new server to the cluster and start moving some of the vBuckets across, moving some of the data across. So instead of having 1024 over 3, you'll now have 1024 over 4. I can tell you that's 256 because I could do the maths on that one. And what we do when a vBucket is moved in its entirety, we make an atomic switch that says, okay, this server is now responsible. And on that atomic switch, we publish a new map to the client that says, okay, vBucket 27, it used to live on server C. It now in the new map, in Rev 2 of the map, it lives on server D. And this lets us dynamically expand and shrink nodes in the cluster. The vBucket trick, this automatic sharding, the 1024 pieces, is also where we get our availability from. So each of the servers, as well as having 1024 active vBuckets, will also have a set of replica vBuckets. So another copy of each of those bits of data. Quick pause there. Does that kind of make sense, that level of indirection, the vBucket map? And this hashing algorithm is where some of that smooth performance gets. So if you ever run a workload across a Couchbase cluster, you'll tend to see that most of the CPU is hovering around a similar kind of level, because everyone should have a reasonably equal set of documents, and as long as you're not accessing the same document over and over again, you'll tend to find that your workload is spread quite evenly. Another bit of the architecture that I won't linger too much on, but we supply a downloadable RPM or Debian install media or Windows executable if you want to deploy in Windows. And every version of the server has exactly the same copy of the software. That includes everything. It includes all of the data service that does these key value lookup operations, the query service that I just mentioned previously, the nickel kind of select star on your JSON documents, a cluster manager who's responsible for serving up the UI, for running all of the health checks to make sure that the cluster is all up and healthy. And so we have this kind of shared nothing architecture where each node you can log onto the UI on any given node, and it'll be there, and each is capable of doing the job. There's no separate special configuration or manipulation. You don't need a separate management node or anything like that. Now, when it comes to actual production deployments, you've got the choice, and this is where performance starts, really, with Couchbase. If you're serious about running a production workload, you should have an estimate of what level of traffic that's going to be. A best case, a worst case, a normal case, kind of the usual sort of think of a number and then probably double it and maybe double it again just for good measure. And oftentimes with larger customers, Couchbase will get involved and help out with the sizing. We've got quite a good frame of reference of what particular sets of hardware can do, how many operations, how many documents it's going to, how big's your data set, etc. And if you want to, you can run each of those different services on each of the nodes themselves in the topology here. But really a more common production deployment is where you choose, okay, you'll do almost an individual sizing exercise for your data service. So based on the size of your data set, how many times are you going to read and write the keys and the values of those documents? How many queries are you going to run? Is it a once a night batch process kind of job? Or if you're running a session store or user profiles, does your user login require a query lookup? Because they'll have significantly different profiles, and likewise for indexing. So I mentioned before, but the data service is the one we're going to focus on in a little while. So when we talk about performance at Couchbase, these are some of the numbers that we're familiar with. We claim, and I think with some justification, that we'll put anyone to the test as being the fastest NoSQL database that's out there. Millions of operations running on hundreds of nodes with terabytes of data across billions of documents. And this is something that I feel very passionate about, and my team are working on continuously, is not only do we we think if we are not the leader, then certainly at the top of the pack, and something that we continue to invest quite heavily in is increasing that performance, doing the analysis. And some of the examples of these clusters in production. So Amadeus, who are responsible for a lot of the travel industry, that traffic I described when you're going to search for flights, ultimately the vast majority of those go down to an Amadeus database that is running Couchbase. LinkedIn, a very, very large footprint. Viber, does anyone use Viber? A few nods. The sort of WhatsApp competitor for doing instant messaging. Again, if you think how many people, millions and millions of users around the world sending messages and stickers to each other, and every time something goes off, it's getting stored in Couchbase. Pokemon Go I mentioned, and Criteo, another customer from France with a very interesting use case of doing real-time ad targeting. So they've got tremendously challenging latency requirements. So when you load a web page, they get asked the question, what's the most appropriate advert I could show this person? And then before the page is loaded, they need to have crunched whatever data they need to, decided on what the best or most appropriate advert is based on the set of information they get given, and determine the advert to be returned. And they have a significant Couchbase footprint. Okay, quick pause there. That's hopefully quite a swift overview of some of the aspects of Couchbase and what it does. Any questions so far on any of the capabilities or the content I've provided so far? Cool.
Hi. I just wanted to know what kind of operating system do your clients use mostly? Do they prefer Linux over Windows?
Yeah, so we supply and we support. So the question was, which operating systems do our customers tend to favor? The vast majority are Linux, and they will run both Couchbase Server on Linux and their clients on Linux. We do have, difficult to put a number, probably in that, I would guess between sort of, I would say 30% or under running Windows, with our .NET SDK is the second most popular after Java in terms of the number of production deployments. So it's predominantly Linux, and a lot of the support we do is based on Linux, but a significant number of Windows users, and both are equally supported. Okay, so next up, let's start getting a bit more to the good stuff. Make all these bold claims about, hey, yeah, Couchbase is the fastest game in town. I want to give you a little bit of the background as to some of the architecture concepts behind the scenes, and then we'll have a look at a live cluster and see what it can do. So mentioned a few of these concepts before. The core of, so this applies to the data service, the key value, the service that's, if you've ever seen Couchbase, it's the Memcache D process. That's the one where you say, store this document or give me this document back. It's the Memcache D process that's responding to you. All of this section is about that. So we've got that sharding in place, which means that all any given node needs to worry about is requests for data and responding those requests for data. We've got an isolation. There's the cluster management, and is this node up and healthy and operational is done entirely separately. So any of the access to your data, we spend a lot of time and a lot of care making sure that the access to that data is heavily optimized. We try and keep as much of your working set in memory as possible. So when you request a document, we'll be able to service that request from memory. And we have LRU algorithms that will sort of slowly degrade data over time and choose which data, if we need to free up a bit more space for new documents or a larger working set, we'll try and evict some of the old documents so they'll get pushed to disk. And over time try and make sure that as much of your working set as possible is based in memory. Now, I mentioned that we have this system of availability so that when a document comes in, it is immediately asynchronous. So let me see if I've got the slide on this. let's go to this one. When a write is written, when a document is written to Couchbase, so this is the client application here. I can rerun that. It'll come into our managed cache in memory, and two things happen asynchronously. So one is it gets pushed into a disk queue for persistence, so we keep the data safe on disk. And secondly, it's pushed to a replication queue. And actually what we find in practice is that the document is replicated more quickly across the network to a second node. It will reach that second node before it's been persisted to disk. Less the case if you're using SSDs, but certainly if you've got a spinning disk. We say actually for resilience and protection of your data, don't so much care about how long it takes to get to disk. Care about how long it takes to get to that second node. It's your replication latency, because chances are if this disk goes down, then the entire node's gone down. So you need to worry about the second node. So when we're advising our customers, we always say, worry about your replication latency before your persistence latency. So, and all of that network transfer is done from in-memory to get some of the performance. We use an append-only file format, so when we do need to write it to disk, again, we don't totally dismiss the persistence latency. When we write it to disk, we want that write to be as fast as possible, and quite a cheap way of achieving that is just appending it on the end, so you don't have to do any file seeks to find the particular place in the file to do that. We pay a slight price for this, is that obviously if you keep doing that forever, then you're going to use up all your disk and something bad's going to happen. So we have a separate process that kicks in now and again that lifts up that file when it's got past a particular threshold, and we'll remove all of the dead space, we'll compact it and create a new version of the file. The price you pay is obviously at that time your disks are doing a little bit more work. You've got to read that file and rewrite it. So there is an increased disk cost. But for the type of workloads we run, we think that's a fair trade-off. So that you get the fast persistence times, and occasionally when you do need to compact the file, a little bit more write overhead. So behind the scenes, this is one layer deeper into our architecture of the data service. So when we go to Node shortly, I'll show you all of the different processes that are running. And this corresponds to, again, the Memcache D process. So one of the ways we achieve that high performance, I mentioned that we're going to asynchronously replicate things across the network. We're going to asynchronously write things to disk. And so we have different threads with responsibilities. So some threads, their only aim in life is to take requests off the network, look into memory and see if they can be fulfilled, and if they can, respond as quickly as they can to the client. And this is what lets us achieve, for those in-memory operations, a response time back to the clients in less than a millisecond. We tend to measure our response times in microseconds. And so for such a request, we have each vBucket has its own hash table. Each hash table has a set of locks on it, so we can access various different portions. So if you remember, your bucket was split into 1024 chunks. Each of those chunks has its own hash table. Each of those hash table has its own locked section. So our locking is done on a very, very fine granularity. So it's very rare that we see performance problems due to lock contention within Couchbase. We have the checkpoint manager is quite an important piece, because that's the component that's responsible for queuing things, and separate threads. So we have writer threads that will read from the checkpoint manager and persist things to disk. We have replication threads that's done by the non-IO threads that will again read from that checkpoint manager and replicate things across the network. Again, a lot of care and attention has been placed on making these lockless atomic data structures that will allow us having multiple threads in action without contending with each other. The number of threads that Couchbase has is sort of dynamically dependent on the hardware that you're running on. So you'll see, if you run Couchbase on a 4 CPU system, you'll see a significantly different count of threads to if you're running on, say, a 16-core system. And I'll show you a quick example of that in a second. And so these are some of the things when we're doing our performance analysis internally. If a customer comes to us and said, "Hey, how do I get more performance? Am I using this database to the best of my ability. These are the sort of things that we look at. We look at how many threads they have, where the time is being spent in these threads. So what we're going to do in a second is run some workload against the cluster. I'll take you through in a bit more detail. If you've never seen the Couchbase UI, it's quite busy. There's a lot of information. It's also available via the REST interface if you want to pull it out and slurp it into your own system. But when we're talking about performance and looking at where performance is being spent, these are some of the key metrics that we look at. First and foremost, how many operations is the database doing? Are you doing 10 operations a second, 100 operations, 1,000, 100,000, million, etc.? How many of them are reads? How many of them are writes? How many of those writes are how many of those reads are being serviced from memory? How many of them are going to disk to fetch the data? How busy are the disks? How big are those checkpoints that I just mentioned? How big are those checkpoints? How many items do we have in the queue ready to be written to disk? How many items do we have in the queue ready to be replicated, etc.? So again, we'll look at some of these. And then the other thing that we advise all of our customers to do is don't just run the workload and then sort of give yourself a pat on the back and walk away. We encourage you to try and break it. We've got this available architecture that says, okay, we replicate copies of your data here and there. We survive node failures. If you're running your cluster at 100% capacity, no matter how good Couchbase is, if you lose a node, then you're going to be in trouble because you've inherently lost some capacity. So when we're asking customers to plan their workload, we say plan for the worst case. Plan for what happens if you lose a node during your peak. What happens if you decide that you need to add capacity? If you need to scale up the Pokemon example where you need to add hardware, you need to add nodes to your cluster. Obviously, we're going to move some of the data around, and there's a small price you pay in terms of the network overhead for doing that. And so make sure that yes, you can still sustain your application, your requirements whilst all of this is happening. What if you take a backup from time to time? Do you still achieve the required performance levels when your backup's running? And again, kind of nice to know, where does it break? At what point do you say, okay, this cluster is at absolute saturation? Because that's going to be useful to tell you when you might think to expand your capacity or split things out some differently. Okay, so that's probably enough talking for a second. I want to introduce my cluster. So this is the Couchbase user interface. I'm running version 4.6, which is our latest GA. You go to couchbase.com/downloads. I forgot to mention, actually, Couchbase, it's fully open source, as many of the NoSQL products are. So all of the code I've just described on here, you can go to. In fact, let's do that while I mention it. GitHub, Couchbase, Memcache D. So in here you'll see all of the C++ stuff, code to deal with buckets, etc. So again, if it's absolutely free to download, to play with it, to set up a cluster and have a go at it and see what you like. Okay, so I have a cluster running. It's got 4 nodes. So I've borrowed some instances from. Does anyone use Google's Compute? No one. Oh, Amazon. Yeah, a few more Amazon users. So our customers predominantly, I would say, use AWS more so than Google. I actually find the Google Compute interface is really nice for. I don't have very elaborate networking firewall requirements. I just want to sort of configure my number of CPUs, number of memory, disk size. I find that my experience with Google is it lends itself to doing that a bit nicely. These are so Google has N1 standard 16. I think I've got the definition of what they are there. So they've got reasonably powerful. They've got 16 virtual CPUs. They've got 60 gigs of RAM, and I've given them a half terabyte of SSD. So I've got 4 of these sat together in my cluster. And a second. I mentioned that we put all data in a bucket. So I have a single bucket, and it's got 250 million and 1 documents in, and I've got 1 replica configured. So every one of my 250 million documents, there's another server with another copy of that document on, so 500 million in total. So we'll start very, very simple and just add a single document. I'm going to embarrass myself with my Python here. Oops. So a very simple Couchbase script, Python script to just put a single document into Couchbase. So I mentioned before we supply various different SD developer kits. So I've already installed the Python developer kit using pip. I connect to my bucket. So for that I give it 2 things. I give it the server, any server in the cluster, and the name of the bucket, and a very simple key, and a very simple JSON document, Python dictionary that's going to transfer to JSON. And that's it. Just do, okay, I've got my bucket, I've got my key, I've got my value, just combine those 3 things and say, okay, into that bucket, set my key and my document. So if I run that, okay, and I've got a result back. And so if we go to the cluster, hey, there's the op. So doesn't really follow when I'm going, oh, millions of transactions a second, and here's a single op sort of trucking away. But there's that famous quote about the journey of 1,000 miles starts with a single step. So there it is, and you can see some other things on the UI here. So you can see the operation that's come in. You can see, I don't know how easy that is to see the disk update, so you can see that's been written to disk. If I look down, so we call it the protocol that replicates documents between the nodes. We call the database change protocol, and I've just caught it in time there. You can see, okay, that's the stat just going out of view for the single document being replicated. So this dashboard gives you a reasonably sort of high-level appreciation of how busy the cluster is. So that was a single op, and if that was my key. We'll just take a look to check. So if I type in the key and hit lookup, you can see there's my document, made it safely in. Okay, so that was a single op. I do that just to show you the sort of the starting point. Now, if you want to write a very high performance application, there's a single golden rule, which is basically go as parallel and as asynchronously as possible. So you don't want to pipeline your requests whereby the next operation you do is waiting for that first one to come back, because you have to send the op, wait for it to get across the network. It'll be processed by Couchbase in under a millisecond, and then it'll come back across the network before you send your other. You're going to have these huge bubbles as the documents go across the network. So we spent a lot of time with the SDKs, providing the facilities to make it easy to write asynchronously. So in Java with classes such as listeners, C with callbacks, and whatever the language's native equivalent is, to allow you to fire the operation off and receive a callback when that operation has returned successfully, so that you can get on and do useful work. You can log in another user, you can do another lookup, you can do something, you can keep yourself busy while you're waiting for the operation to go across the network. So if the first rule of acquiring performance out of Couchbase is make sure that your application is, to as large an extent as possible, doing operations synchronously. Now, it's not always the case that that's possible. Sometimes the next operation requires the result of the previous one in order to do the right thing. But if you're if you're a session store or a user profile, you can be logging on other users. You can have a batch of things that you need to process. You don't necessarily have to limit it to one at a time. And the ways that you achieve that depends on the language. You might have run multiple instances of the client. You may run the paradigm of the language itself. Java lends itself more to being multi-threaded, etc., rather than having, you might have 100 Java threads rather than 100 individual Java instances. Some clients run hundreds and hundreds of different application servers that all have a single instance of a client running on them. Others have the inverse. They have a single client server running hundreds of threads that are all talking to Couchbase and making connections. But either way, the aim of the game is to get as many things and keep the database as busy as possible. So I'm going to turn things up a little bit and show you one of our load generators. So this comes with this is a C-based load generator. It comes with our C developer kit that we supply. It's called PillowFight, and very useful for generating a lot of key value traffic very, very quickly. It's a bit of an animal. It's you need to, in a recent edition, they introduced a very useful rate limit, which just put a few reins on it, because otherwise it would run amok. And so this lets you do kind of the basic things that you want to do from a load generator. How many documents are we talking about? How many reads and writes to those documents? How big are those documents going to be? It lets you tune all of these different parameters. And so, and the batch size, which is a cheap way of simulating many clients at the same time. So rather than having 1,000 different client servers, I can tell PillowFight to just dispatch 1,000 operations at a time, just as a quicker way of generating some load. So let's do it. Let's this one here. Whoops. Need to give it some options. So a bunch of parameters. I'll just pick out a few. Minimum size, maximum size, number of items that we want to attack, a prefix so you can segregate your data set, and a number of threads. And again, I'll get the ball moving very, very, very slowly. So if we give again, it needs, in order to connect, it needs the two parameters. It needs a name of the server in the cluster and the bucket. And give it a working set of, so we've got 250 million items in the bucket. So we use, let's say, a working set of 10% of that, 50 million. Going to do 256 byte items. Just a single thread and one operation at a time, and we can see what happens. Okay. So back to the cluster, we should start seeing a bit of traffic coming in. So you'll see at this stage we're doing about 4,000 operations a second. If I show you the memory, each of those nodes is using about sort of 13% of the CPU, so or less than 10%. So they're a little bit bored at the moment. The other thing I've noticed that all of my operations are sets. So each of these is a write to the cluster. That's because I forgot to tell it that my data set was already populated. I think it's no population. Okay. Oh. And just to keep things consistent as we go through these, we'll give it a read-write ratio. So typically, there's a couple of common ones. One is 100% writes when you're just firing data into a cluster. Another is 50-50, where you have an even mix. Another one's most common is probably about an 80-20 of reads versus updates. So I think something along those lines. Didn't like that. See if I've got that the right way around. Okay. So my overall operations a second. I'm doing a similar sort of number around about that 3,000 mark. Cluster still at less than 10% utilized, and that the majority of the workload, the sort of 2,000 or so ops there, gets. So I've got that 80% are doing reads and 20% doing sets. So clearly, if I'm looking at this, I'm thinking, well, I've got 4 servers here. They're losing less than 10% CPU. Clearly, this cluster can do more. Barely sort of scratch the surface. So, but that gives you a nice sort of baseline that says, okay, we're on the board. So what we can do is crank it up. Let's see what happens if we create 8 threads now. So this is the load generator is going to spawn 8 instances, 8 threads of itself up, all basically doing the same thing. And it's going to share out these 50 million documents across those 8 threads. Okay, so now you can see we've jumped to about 20,000. Oh, that gets a second. Sorry. Look at the total operations. About 25,000 operations a second that are being driven by this load generator here. Let's see if we can find some other interesting. So you see now that we're doing a little bit more. We're up to sort of between sort of 15 and 20%. So maybe it's a good time to start looking at what's going on. So I've got a session console. Yeah. Yes. Oh, it's absolutely not CPU bound at this juncture. It's the bottleneck at the moment is the client and the amount of traffic that the client is putting on it. It's exactly what we're looking at. How much headroom does the cluster have to go a little bit further? Can you see that at the back, by the way? Is that? Yeah. Okay. So all the process is running as the Couchbase user. You'll see there's the Beam is an Erlang process, so that's responsible for, amongst other things, the cluster manager and the UI. Have there the indexing, the query engine, and the one I'm interested in is right down at the bottom here. This 2774, which is the Memcache D process itself. So that's the one. If we just look at a quick top on the system overall, you see of my 16 CPUs, it's the Memcache D process. That's as you might expect now that we're doing key value operations, the Memcache D process that's responsible for those key value operations is using the most CPU. So let's dive into and see what that process's threads are doing. So for top, -H, -P, for the PID 2774, I think. Okay. Oh, looks pretty horrible. Okay, so we've named all of each of the Memcache D threads. We've given a name, so it's easier to sort of pick out what job it's doing. So writers, as you might expect, they're responsible for writing the documents out of disk, taking the things off the checkpoint queue. So if I sort by, see the non-IO threads, so they're responsible for doing the replication. Each of those are using. Actually, if I sort by PID for a second, okay. So the non-IO threads, they're the ones that replicate when a document comes in. They're replicating it to a different node and receiving that replica on the other. The writer threads responsible for pushing things down to disk, and the worker threads, these ones, are the ones that are responsible at the front end. They're catching the operations from the client and putting the writes in the hash table, reading the reads from the hash table, etc. And looking across the board, there's nothing. Again, if I sort by CPU, as you might expect, there's nothing particularly hot. What we're looking for is something that's like permanently 80% or beyond. And that suggests there's some sort of resource constraint, that something's doing a job and it's got no additional headroom. So again, let's go back to this and turn up the heat a little bit. So now I'm going to, I mentioned that we've got this batch size parameter that says, okay, instead of doing one operation at a time, let's do n operations at a time. So let's turn it up to, let's say, 100. So in theory, we could be doing up to about 100% 100 times the workload that we're doing before. Okay, cool. So now CPU has gone up to 60, 70%. So it's making each of those 4 servers in the cluster worker a little bit harder. We were doing about 350,000 operations a second there. And so if we flip back and look at what the threads are doing now, it's the same culprits. It's the workers, the writers, and the non-IO threads. Sure.
Sorry. Can you show us on your laptop how much bandwidth does it take over the network to send all those requests, reads or writes, stuff like that?
I could try.
Okay.
IF top?
No. You just have the system monitor, I think.
So none of this is running locally.
Even the script.
Yeah, no, that's running on a client on a Google computer.
That was the question about. Just to know how much traffic does it generate, the script.
So I don't know if anyone always. I must admit, at this point, I just quickly like to check my facts with a Stack Overflow or something like that, just to make sure I'm looking at the actual right number. But I think there we are reading about 60 megs a second and outputting 145 megs a second.
Okay, thank you.
On one node. Good question.
So that is the traffic that reaches out the node. But what about the traffic from your laptop to internet?
Nothing. So that on the client.
Yes.
I could open up actually.
You have system monitor. I think it shows you the.
Yeah, but sorry. This client is. I've SSH'd into a client machine on Google Compute. So there's no traffic coming out of
okay.
here. There's no.
Okay, that is the question we're asking ourselves, because we're seeing a lot of traffic and we're thinking what kind of connection did you have from your laptop today?
All right, yeah.
Yeah.
nothing special.
Okay, thank you.
Okay, so the last experiment is just to say try and find the breaking point. So slam this up to. Turn the dials way up, so twice as many threads and 10 times the batch size, just to see what happens. Again, we encourage each and every one of our customers to do this, to, like I said before, find the breaking point. What's it that's going to go wrong? Okay, so here we are. We've got these 4 nodes that are doing, I don't know, what's that? It's maybe going to level out at perhaps half a million operations a second. You look, the CPU now is pretty red hot. we're clearly running these nodes close to their limits, and doing. But we're keeping a reasonably steady disk write queue, which is obviously you don't want to be in the case where you're writing faster than your disks can keep up. So the fact that that is proportionate to the number of, it's not up in the millions, it's pretty proportionate to the number of writes that the cluster is receiving. Likewise, the replication queue, we're receiving 120,000 operations a second, and every time we check the queue, there's less than 20,000 items in it, which shows that we're managing to replicate at a fair rate. And if we look back at what some of those threads are doing now, we should start seeing, okay, so some of the workers, so these are the ones at the front end responsible for taking those ops and replicating some of them out. Some of them are running at sort of 90%. And this is a sign that, okay, this cluster is kind of approaching its limits at this juncture. So what would be very unfair would be if we just killed a node. So if we just decide to fail this one, hard failover. Actually, before I do that, I just want to check what number of ops we were doing. What does that say? Okay, roughly just 500,000-600,000 ops a second. And so if we go and just kick one of the, oh, you can see the compaction's kicked in. So this is this process of going, okay, I've reached my threshold. The disk has got to a certain point where it's decided, okay, I'm gonna need to make a fresh copy to free up some of that disk space. So that's an interesting test to make sure that we're capable, the level of traffic that we're capable of sustaining whilst compaction is running. So what we need to do, let's remove number 4, hard failover. Okay, so it's not doing too bad. It's still trucking along at its 400,000 ops a second, even though the number of nodes has gone down. You'll notice that if we look in the vBucket resources, now that we've kicked a node out, we still have our 1024 active vBuckets. We still have a full copy of the entire data set, but we've lost some of our replicas because we've burnt some of those spares in essence by taking a node out of the cluster. And so the other nodes that had a spare copy of that data have said, okay, right, now my spare copy is the active. And so that's why at this moment we do have all of the active data, but we would need to rebuild some of those replicas. And the way we rebuild the replicas is hitting the rebalance that's going to go and spread that data, those vBuckets, evenly back across the remaining 3 servers. Okay, so that's not too bad. I've got three servers there that are sort of repairing themselves. They're shuffling the data around. We're doing round about sort of half a million operations a second, which isn't too bad for 3 CPUs. Okay, couple more things to mention. One is, okay, well if when you hit some sort of capacity. How about tuning? What can you tune? So each of those threads, I mentioned that we dynamically create those threads depending on how many CPUs you've got. But they are all configurable as well. If you decide, actually my workload is so write heavy, I need a few more writers than you give me by default. Or I've got that many operations, that many clients connecting, I could do with more workers at the front end that are servicing each of these requests. Then you can tune those. We always say that premature optimization is pointless optimization. There's no point tuning for something until you've actually seen it, and you can measure do the good science of measure the benefit before and after, and make sure that you do get an improvement. Scale only the portions that you do need. So mentioned before that if you're doing a key value workload, there's no point adding more query nodes to your cluster because it's not going to help you. The most common thing that people do tune is actually the task itself, particularly those that are deployed in Amazon and Google, etc. The ability to add a new node and just rebalance it into the cluster is actually quite often the easiest way of solving a bunch of problems. For query workloads, there's often tuning that can be done on the precise index. Okay. So I'll probably finish there with a few points. So hopefully, I mean, it seemed like most of the audience were already familiar with NoSQL. Hopefully it's given you a bit of a flavour for what Couchbase brings to the party and how we do some of our internal sort of performance assessment for customers for some of these big peak workloads that they deliver. I'll finish there. Thank you. Any questions? Question at the front?
Thank you for presentation. In your demo, do you have any way to track the latency of the requests? So, how long do they take actually when it's on the load?
Yes, PillowFight has that built in. I don't. So I could try it. Let's see. So it has. Actually, I need to quit that. Sorry. That's better. Okay. I think. Let me see. So the question was, okay, that's fine for what your throughput's like, but what about the latency? -T gives you timings. I don't know if they come out periodically or at the end. So if we run the same command and stick a -T on, let's see what happens. Okay. So let me just let that run for a few moments, then kill it. So PillowFight is measuring the time from when it dispatched the operation to when it got the response. Okay, that's probably good enough. Okay, so we can see that the majority came back in sort of 10 to 20 milliseconds. There were a few long outliers that were just under half a second. Sort of the 90th percentile latency, but yeah, between the majority there between 10 and 20 milliseconds across the network.
But that's on the local. Basically, it's a local connection. It's on the same.
Yes, that'll be going off the 10.Google internal network.
Okay. And the second question is, how does that scale with the number of connections to the servers? Because you've piped everything to a single connection, which is pretty much the best case. What happens when you try to have a lot of TCP connections coming in?
So each of those threads will make its own TCP connection to each of the nodes. And I would actually say the opposite, that having a single client responsible for receiving and handling all of the interrupts, it would actually probably be a far more favorable test and a better test if I had 20 different client servers that were all capable of. I think the client, when you've got that many operations going through a single client server, it's the client that's its network stack starts to feel under pressure. And so yeah, I think when each of those, how many did we have in the end? 16 threads. So that would be 16 TCP/IP connections to each of the 4 nodes. So we would see 64 outgoing connections from this client machine. But we have a cap of on each of the servers of 30,000 connections. So, and it doesn't really, because of the sort of the round robin. We use libevent, the C library to round robin between the connections, and it's actually, it doesn't, for our purposes, it doesn't really make much of a performance difference. We still need to service the op, and we don't really mind if it's on a different connection or not. It's the rate of operations rather than the number of connections that's the biggest determining factor. Is it? Any other questions? Sure.
I was just wondering, given the fact that you have a lot of statistics going there, like a lot of feedback, is there any impact of on the node's performance if you want to drain a lot of statistics out of the node?
Good question. So the statistics collection is done by Erlang, the cluster manager, and it has this lossy calculation where it keeps all of the stats for the last, every second for the last minute, every minute for the last hour, every hour for the last day, etc., going back years, I think. I mean, this cluster's not been, it's not been up that long. But if you were to, so they, internally we're collecting the stats from each node once a second, which is probably the level of granularity that most people need for their own monitoring. Now, and so that doesn't really face that big a performance impact. But for sure, you could probably be like a little bit devious and create a script that just perpetually, like, I don't know, thousands of times a second hammered it, and then you would start to see a difference. But at the level of monitoring that's useful, I don't think it has a performance impact.
Thank you.
Sure.
So Couchbase documentation strongly recommends to use JSON as a format for the values. Why is this? Do I need to use JSON if I use key value storage? So it comes with additional space. So if I choose some binary format to save space, does it help with performance?
Yeah. So for key value, you're absolutely right. And a lot of our users, Viber, for example, who are storing text but only use key value, will actually use their own binary format, like protobuf or something like that, to make it smaller. The advantage of keeping it as JSON is for if you want to query it or you want to index it. If you don't want to query or index it, then binary is absolutely fine.
Okay, so and one time I discovered the benefit of compressing data before putting it into Couchbase. So is it a common use case so that it might help to compress the data? And if it is, then why it's not in Couchbase distribution by itself? So the ability to compress data before putting to the server.
Yeah, it's a good question. And so we do compress when we put to disk to save on disk space. We don't yet actively compress in memory because for we could do, but we leave that responsibility to the client. We like to keep it nice and simple and fast, and so if the client wants to compress the data because it's worried about the network bandwidth or the space it will consume in memory, then there's no harm in compressing it on the client. Certainly, it's something that we've considered, but there's never been a use case that's sufficiently demanded that, hey, that couldn't be solved by just going, well, actually, if you use another node, then you've saved all the space that you would have compressed. But we do compress on disk.
And so, what is the value size for which Couchbase works the best? Is it kilobytes? So, how much? How many?
Whatever you want. For some reason, and this is like a legacy reason, we have a 20 meg limit on the size of document. Just because if you want to do high scale document databases, what you're putting in your documents that are larger than 20 megs. I mean, there is the ability to increase that limit if you absolutely want to. But in terms of there is no, beneath that 20 megs, there is no optimal document size. It's not like we work better if it's 1K or 10K or 100K. The questions there are really about storage space, network bandwidth, etc.
Hi. First of all, I would like to say that I found impressing the demo with a small cluster of just 3 nodes handling 400 kilo requests per second. My question is, how does Couchbase compare to Cassandra, for example, which claims to be one of the fastest NoSQL database nowadays?
Yeah, so very good question. One that comes up very often. Benchmarking it's a horrible business because everyone claims they're the fastest. And if you put me next to someone from Cassandra, they would say we're the fastest. I would say no, you're not. We're the fastest. There have been efforts to. You're familiar with YCSB?
Sorry?
YCSB. There's a trying to standardize on a benchmark, but it's the best one there is, but it's still not a very good benchmark. It does key value, it does a bit of querying, and so the specific answer is it normally comes down to what the workload is, and what your requirements are. The other bad bit about benchmarking at the moment is everybody, when they publish a report, they always benchmark the competitor using some like a questionable configuration, a questionable version. They've not and you go, come on, it's not a fair fight. It would be really nice if we could go here's the workload, you configure your thing, we'll configure ours, and then let's meet up. And YCSB tries to do that a little bit, and we would say the results show that we're better. But of course, the Couchbase is going to say that. I would say honestly, their reputation is if you've got a heavy write workload with large documents, then and you care about how long it takes to persist on disk, then they might have the edge in that case. But for something like that, we did, they published this is about 2 years old. They did a study with Google on how many of their nodes would take to do 1 million operations, and it was hundreds of Cassandra nodes. And and I was fair warning, I was part of our response to that. But we tried to match them like for like number of documents, number of replicas, node size, number of clients, everything. And we did it on 50, which and a fraction of the price. And so,
do you think that this difference could be explained by the fact that your product is coded in C and their product is coded in Java? Because at the architecture level, I find a lot of similarities between both of them.
Yeah, for sure. I mean, there is a reason we passionately stick to C and C++ and aggressively adopt the new features in C++ 11 and beyond that will give standard the atomics, the libraries, the infrastructure that the libraries provide for the better performance. Anytime we can remove a lock from one place or another. Very quick aside, just because you mentioned C++. Had this bonus material. I want to walk you through it very quickly. We had a problem that one of the other developers raised, where the cluster manager was telling us the state of a vBucket. This vBucket is active, it's replica, it's dead, etc. And in certain circumstances, we were persisting that out of sync. So the order that which meant if you restarted and we looked at disk, we occasionally got the order wrong. So this went into 4.6.0. We fixed this, and it ended up for quite a simple problem. It ended up being a major change. This patch of 39 files, 1,300 lines, etc. brand new unit tests. So we fixed the bug, and it ended up being quite a big patch. And we thought, okay, that's the bug fixed. But then there was a surprise. And the surprise was that the performance had gone down. So 4.5.1, which was the predecessor to 4.6, that one patch, we lost 30% performance for the benchmark. A very similar benchmark to that. How many operations can you do? What's your throughput? We lost 30%. So we had to spend the time. We care so much about performance. We obviously did the investigation. And it turned out to be this bit of code here. Just that patch alone. Now, that's added 2 lines of comments and 1 additional variable. So no other change, no code using that variable, just the addition of that variable dropped our performance by 30%. And the reason being, so unfortunately it took quite a lot of time to analyze. And it was this, it was false sharing as the name of this class of problem, where 2 CPUs working on different threads were trying to access stats that happened to be on the same cache line. And so when we put this other variable in, all of a sudden it changed the cache line layout. And these CPUs were trashing each other's cache line to try and get to the variables that they needed. And so it was this kind of quite a long and involved problem that you would struggle to get to this level of detail, we think, in some of the other languages. But with tools such as Perf and all of the C++ instrumentation, finally figured it out. And then the good news in the story is when you know which are your hot variables, then you can use that to your advantage. And actually, we did we deliberately spaced the things out so they would occupy separate cache lines, etc., and reduce the contention. So actually, we took that 30% degradation to our advantage and got a little boost in 4.6 because of that. But certainly, like when we look at some of the, I mean, garbage collections are an obvious one, and you have to be a pretty high standard of Java to understand how to control garbage collection, the different forms where it kicks in, etc. And we have a C++ legacy anyway, so it's quite an easy choice for us to maintain that. And yes, for sure, we'd like to think that it gives us a performance advantage over other Java-based products, etc. But I would say, in all honesty, like I say, it's reasonably. You can download Couchbase and set up a cluster in probably less than half an hour. A simple wizard to click through, create a bucket, and actually you saw my Python effort to create some load. So I would encourage anyone to do the Pepsi challenge and just put them side by side for your particular workload and see what performance you get out of the box. Because you can't always trust the the people providing it to do the right thing. Question. Thank you. Cheers.